Okay, I'm making this video to go over midterm part 2. So we went over midterm part 1 in the other video, and I want to go over midterm part 2 also. And mainly doing this just so if you're still struggling with the concepts, you'll be ready for the final. It's very important that you understand how I did these problems because they will come back. And I don't think just simply looking at my solutions may leave you with some questions. So let's go ahead and do this. So on the screen, you can see I have the midterm itself. So let's look at the first problem. So we have our 20 kilogram uniform circular rod OB and loaded as shown with the two loads. And the thing that is also there is the rod weighs 20 kilograms. And so 20 kilograms is very small compared to the loads on it. And I noticed that was a issue with for many of you not having the correct units on the 20 kilograms or completely ignoring it altogether. So make sure that you look at everything that's there and make sure that you account for it. So what we want to do is we want to just replace the two loads that are applied at A, the weight of the rod and the moment applied at B, with a single force couple system at O. So remember that whenever you see replace with a force couple system or replace the forces in moment with an equivalent, that means that the answer has to contain the force and the moment. So it's not enough just to give me the moment, you have to give both. So let's go ahead and do this. So here's my drawing, and I don't expect your drawings to be this neat on an exam. On the final, you'll have more time, so try to make them legible. But again, the important thing is that we get everything down that we need. So we can see that I have the two loads, 20, 50. We have the 150 kilonewtons. I have my vector G for the weight at the center, and then I have the dimensions. So all dimensions are in meters. So and it gets kind of messy if you put meters in here. So sometimes I'll just simply write dimension and then meters. Okay. So, and then weight or force in kilonewtons. So again, on exam, you may not remember to do that. So, I know what you're trying to do, but again, it's always important to have units at the end of your, in your answer. All right, so let's look at this problem. So we know that we need both a force and a moment. So we're trying to find the moment and the resultant force. And so the first thing we're going to do is we want to figure out what our forces are. So we know we have the tension on this AD and we have the tension on this AC. So we know that tension AD is going to be equal to the scalar value AD times the unit vector AD. So I know that from looking at the diagram that my AD is going to be -3 in the I. So I'm going that way, and that's the negative X direction. -4 in the J, going back that way, and plus 3K. So I'm going up. So always going from here to here. And that may seem really simple, but a surprising number of issues with directions I saw with different people on the test. So don't pay attention, make sure it's clear. So you have that. So we'll go ahead and multiply and get our denominator, which I'm just going to put as root 34. So that's just everything, the magnitude of those. And then I'll go ahead and multiply that through by 50. So I know that then if I say TAD, that's going to be equal to 50 kilonewtons times this. So -3 over root 34 I minus 4 over root 34 J plus 3 over root 34 K. And that gives me an answer of -25.7 I minus 34.3 J plus 25.7 K. And we know it's in kilonewtons. So then we'll also do the same thing, TAC. So for TAC, we know it's just going to be the scalar AC times lambda AC. Now in this case, if we look at AC, we see that this is 4 and that's 3. So this is a 3, 4, 5 triangle. So I'm just going to go ahead and write what that is because I know you guys can do it. I know that you can see lambda AC then is just simply 3/5 I minus 4/5 J. So my value then for that becomes 12 I minus 16 J. And that's in kilonewtons. All right, just like this is in kilonewtons. All right, so that's pretty easy because that was just 20 times 3/5. All right, so we have our forces. So we also have our weight. So our weight, and that's gonna be minus 20 kilograms times 9.8 meters per second squared. And that's in the K direction. And so we end up with minus 196 newtons. And if I put a K there, we don't want it to be kilonewtons. It's just minus 196 newtons. So since we're dealing with kilonewtons, this might be easier just to say it's equal to 0.196 kilonewtons, all right, in the K direction. So now what I'm going to do is I'm just going to add these forces up, this plus this plus this, because those are the 3. And if I add them up, my force total, and I'm going to just do this because I know you guys can do this, no problem, but you end up with minus 25.7. Sorry about that. So, sorry, I got out of there. And then minus 25.7. And then you have the 12. And then you have minus 34.3. And that's minus 16.0. And then plus 25.7. And you have 0. And then the only other one you have is 0, 0, negative 0.196. All right. So if you add all these together, you get your F total equal to negative 13.70 I minus 50.3 J plus 25.5 K. All right. And that's in kilonewtons. So that's one part of your answer you want to make sure you got. All right. Good. So now what we're going to do is leave that up there best I can. And we're going to go ahead and figure out what the moment is. Now, we know that for the moment, again, we're trying to find the moment about O. And since both these forces emanate from the same location, then we'll just take a moment about O and we can just add those two forces. We don't have to do a separate. And I noticed some people did that. And that just creates more work. You can just add the two forces and take them at the same time. So that said, if we just add tension AD plus tension AC, right, which was just the forces we had before, then we just end up with negative 13.70 minus 50.3 plus 25.7. So of course that little bit of weight really didn't do anything. So, but it almost could have been neglected in a sense because the amount it was relative to the other forces. So, but there we have that. So that's our load, or I'm sorry, a load from the tension. And we know that R A relative to O is going to be equal to 4J, and R W, or say G, because that's the point, G relative to O is equal to just 3J. All right. So if we set it up, our moment about O is just equal to 0, 4, 0, negative 13.7, negative 50.3, 25.7, and that's plus. So this is my A relative to O, right? Because that's where these emanate from. Plus 0, 3, 0, 0, 0, negative 0.196. And we're not setting equals 0 because we're looking for the resultant. So we'll go ahead, do our cross, and we end up with 102.9 I plus 54.8 K minus 0.588 I plus 150 J. And that's what we get from all of this. So our final answer then is 102.3. Many of you didn't account for that. You had 102.9. That's not correct, because even though you can get rid of it because it's small, you shouldn't, because at this point you don't want to make those assumptions. So 102.3 I plus 150 J plus 54.8 K. Now, the 150 J, remember, I can put that in there, but that came from this. Remember, we had that free 150 J. You can tell it's going counterclockwise, so it's positive. So that just gets added in with everything else. And I'm sorry if this is, hopefully it's not too blurry. But so that's what you get. So you get that plus that plus that. So this should really have, for proper sig figs, that should be 0.0 J. And the units on that, of course, are kilonewton meter. All right. So that's how you do that one. So let's go ahead and we're going to do number 2 now, because I want to make sure you understand that one. So here's the second problem. And in case we're not, let's go ahead and look at it on the test. Now, one of the things I want to point out here is this part that says, note the hinge at A cannot support an axial or lateral load. So what does that mean? Like I explained in the video, that if you have a bearing or any kind of rotation, axial would be along that axis. So the axis that it rotates about. So in this case, we're told it cannot support an axial load, but we're not told anything about B. So if we're not told anything, then we assume that B can, all right? So that does have an influence on our free body diagram and how we go about the problem. Now, when we're doing our free body diagram, we start off, and again, it's difficult to put all the dimensions in, so make it as simple as you can. So we have CD, we know that's the tension. We know that this is B, that's A, and we know we have this and this, these two forces for sure. And then once we look at the fact that A doesn't have a lateral, that means it has nothing there, but we have to add in this here. So now we have, and label them. This is BZ, BY, and BX. Sorry, that's kind of tiny. And then you have AY and AZ. Okay. So the dimensions across there are written here, 0.4, 1.5, 1.5, 0.4. So we have the window is shown. We have, and this is all in feet. And we know the window weighs 63 pounds at W. So what we're trying to do is we're trying to find the tension. So we want to find tension DC, or CD, and that's a scalar magnitude. It's not a vector. We know the direction of the vector. And then, of course, we want to find A and B, the reaction. So we have 6 unknowns that we're looking for right now. So again, following the way that I told you, first thing you want to do in a problem like this is you want to have your governing equation. All right. So because B has the most unknowns, let's sum the most about B. Now, some of you solved it by solving for CD by summing the moments about this line. That's fine. that gets you CD, but then you still have to go back and some notes about one of the points. So it's an extra step that, and especially when you're pressed for time, that wasn't necessary. You can get everything you need by starting by summing around B. All right, so let's go ahead, sum our moments about B to 0, so BB. So we have, and just so we have extra space, I'm going to use that up here because we all know that's what we're doing. All right, so we know that we have R, A relative to B, going from B to A, and that's going to be crossed with the reaction at A, whatever it is, plus R, D relative to B, crossed with the tension CD. Now I chose ICOs going from B to D because it's easy, but again, remember that you can go from any point, from B to any point on there. So you could go down to C also. Those are probably the two easiest to find. And then plus R G relative to B, and then that's going to be crossed with the weight. And all that we know is equal to 0. So that's what I'm looking for. I wanted to see that. So that's a big part of this problem was for 50 points. If you got to this point and a little farther, you probably got 25 points of it, because this is what I want you to show. I want some numbers too, but you had to at least have that. So if we go ahead and let's figure out what is our R, A relative to B. That's going to be equal to 3I. Because if I'm going from B to A, I just go over 3 feet. So, and then R, D relative to B is going to be 1.5I plus 0J plus 2K. And then lastly, G relative to B with the weight. And that's going to be 1.5I plus 1.1J minus 0.9K. And notice I'm not worrying about sig figs here. I just want to get the numbers down, make sure we have it. So I also, we have the dimensions. We were given the TCD, I believe. So we know that the tension CD is equal to the scalar CD, and that's going to be multiplied by 0.397I minus 0.460J plus 0.794K. All right, so now we're ready to set everything up. We just have R, A relative to B, and our A. So if we set that up, we have 3, 0, 0, 0, AY, and AZ. That's what we're trying to find there. Plus, and we have R, D relative to B, and that's and then tension CD. Now I'm not factoring these out, I'm just identifying what they are. In some cases, you'll see the scalar value factor out, but I prefer to keep it in. It's just a matter of preference. So we have, in this case, 1.5, and that's 0.397 tension CD, 0, negative 0.460 tension CD, and 0.794 tension CD. All right. So these are just identifiers. They don't have anything to do with calculation. They're just to say what's in there. All right. So you have these in there now. Good. So plus, and then our other one is going to be, of course, R, G relative to B, and that's crossed with the weight, and that's just 1.5, 1.1, negative 0.9, 0, 0, negative 63. And all that equals 0. Okay? So the rest is just algebra at this point. What I found when I did my cross products was that once I did them and segregated them, I got all the I components was 0.92 times tension CD minus 69.3 equals 0. All right. And my J components were negative 3AZ minus negative 0.397 TCD and plus 94.5. That all equaled 0. And then for K, I ended up with 3AY minus 0.69 TCD, all that equals 0. Okay. So I noticed in some cases people would have this and then it'd be like plus that. Now, if that's the case, then this has to be negative, right? Because if you move it to the other side, it becomes negative. This becomes positive. So something has to. TCD cannot be negative. It's a scalar. It has to be a positive value. So, but AZ, AY can be. So if we solve here, we get TCD, and that gives us a value of 75.3 pounds. We can then plug that into here, solve for AZ. AZ is about 21.5 pounds. And then we can substitute 75.3 in here, and we get AY, and it's equal to 17.32 pounds. Okay, so we're not quite done, but what we end up with then is the last part is just we sum all the forces. So if we sum the forces in the X to 0, we know in this case we have BX, and what's our X value? Well, the only X value we would have would be plus tension CD. So tension CD, so it would be, what is tension CD for X? It'd be 0.397. So plus 0.397 times 75.3. That equals 0. So the only other thing in the X is that. So BX ends up being negative 29.9 pounds. Then if we go to sum the forces in the Y, then we have BY, and then that's going to be plus AY, and then that's going to be minus 0.460 TCD, right? So you have to have the Y component of that. So we know this is 17.32. We know this is 75.3. So that equals 0. Therefore, we can deduce BY as 17.32. So BY and AY are the same. And then lastly, BZ. So sum of the forces in the Z. For that, we have BZ. And we're going to minus 63 because that's the weight, plus our 0.794 tension CD, and then plus AZ all equals 0. So we know it's 21.5. We know that we multiply 75.3 to that, that ends up being 59.8. If you put 75.3 in here. So we solve, we get BZ equal to negative 18.30 pounds. And I'm sorry, it's off the board. So there you have it. So there's your 6 unknowns done. I know it's it probably took a little bit of time to power it through, but again, if you could get to this part where you set everything up, that was it. I mean, that was most of the points there. And then, of course, getting the rest of this and taking the time to do, of course, is worth something, because those of you that did it and forsaken don't know if that's the right word, but didn't work on other problems as a result, then it's not fair if you don't get more points for finishing it. So anyway, I hope that helped. And if you have questions, please come to office hours. Thank you.